Now if you have E is itself is 0, so no issues. Now only C remains. For C we have 2 plus 1 plus 3, that is 6. And if any other shorter path is possible, no, it was not possible. So and hence, so it is just choosing the older one only with the updated cost, and that is via A it will reach C with the cost 6. So this is what your answer is. Any doubt up to this? Any doubt in the distance vector? Okay, that's good. Okay. This is the theoretical question that radio waves bounce off the ionosphere, which that actually uh, if low frequency waves are there, they will follow the curvature of Earth. But if it is a high frequency signals, then they will bounce off the ionosphere. This is a theoretical question, and the answer will be high frequency band. Low frequency, medium frequency, and very low frequency is very low frequency. I mean, they are following the curvature of Earth that we have also discussed earlier. So answer will be this, and guided is not the answer. It is radio waves themselves are unguided ones. So this is just extra option. Okay. Which field will change router to router? So version will not change. Identification cannot change. Protocol will not. Version is what which version of IP that will not change. Identification must not change. Otherwise, how will you defragment them, right? So protocol, that is to which upper layer process it has to be delivered, that cannot change. Because it is end-to-end information. It cannot change router to router, right? So that the source address of course cannot change. Router cannot change the source address. Source will be the same. Of course it has to be delivered to the destination, so it will not be changed by router. Only the thing that will get changed is checksum. Why checksum will change? Can anyone tell me why checksum will change? Because of which reason the checksum will change? We have discussed this in class. At every router is checksum is computed. Why? That is what my question is. Okay, that here it is answer is correct, but you should know why at every router checksum is computed. No, error control is okay, but that is not that is fine. But even though if it is not meant to be, I mean, due to recompute, the value will be different. Yes, TTL is decremented. True, TTL is changed every time. If TTL changes, the header changes, and hence your checksum has to be recomputed, right? So it will not like it will compute and verify, and it will remain same. It will change, right? It will change. Um, Host to host, because every router is going to decrement TTL by 1, and hence IP header will change, and hence checksum has to be different from the previous one. Okay, which of the following statements are true for optical fiber communication? So the attenuation is less, right? So it is not true. Difficult to tap, yes, fibers are difficult to tap. And it supports higher bandwidth. Again, this is theoretical question. Yes, it supports a higher bandwidth in gigahertz, that you know. And it is less affected by this chemical one, so it doesn't get affected easily. So that will be false. So this two will be true, others are false. And again, this is ISDN question. Data and channels are used for the controlling and signaling purpose of the barrier channels. So answer will be the data channel in ISDN is useful for controlling and signaling. So up to this is the end of your paper. And any doubts so far if you want to discuss anything? Otherwise, I'm interested in starting the next topic. Anyone having any doubt here? Should I move to the next one? That's great. So now we are going for the next question, next topic. See, this is very interesting protocol now. Routing protocol we are learning. Which routing protocols you have studied so far? Which routing protocols so far you have studied? Have you studied any routing protocols? Have you studied any routing protocols? Yes or no? Do you know what is routing protocol? Okay, routing algorithms. Let us start with routing algorithms. Have you ever studied any routing algorithm so far? Which routing algorithms you have studied? Which routing algorithms you have? Flooding, true. Flooding is one of the routing algorithm. Distance vector, true. Shortest path, true. That's true. So these are the routing algorithms that you have studied so far, right? Protocols again are not in your syllabus. We will not going. We will just discuss algorithms, and the standardization of those algorithms is the protocol, right? Like what is the standardization, right? In the distance vector, you know that distance vector is shared by the neighbors, right? But when they are shared, when the distance vector is shared, what is it? What is the timing? Your neighbor shares the distance vector, right? So when they share, it is periodic. That you have studied, that it is periodic. Periodically we share, or any change in the network happens at that time we uh, at that time we what we can say, we are sharing this information. See, every neighbor has some information. When any update occurs in that neighbor's information, then they are sharing with the neighbors, or periodically they keep sharing, so that any router is down or something, they will get updated by the new ones, right? So what is protocol now? Protocol is that it will decide that periodically, that means how many seconds, 2 seconds, 5 seconds, 5 minutes, 5 hours, or 5 days, right? So that is what the protocol is, right? And what are the protocol says, okay, you will share the information, but how many fields, how the information is, whether it will be encrypted or not, all those things are nothing but in the protocol, right? So but right now we are not interested in the standardization of the things. We are interested in the learning the algorithms, learning the methods, right? So we were going for the next learning method, that is link state routing. What was the problem with distance vector? What is the problem with the distance vector? Count to infinity. Have you heard about count to infinity problem? Yes, count to infinity is the issue, right? Count to infinity is the problem of this distance vector, right? So we need to resolve that issue. We need that, and another issue, if you remember, that it we were not having overall view of the entire network, or rather I should say, because I am taking information from my neighbors only, right? I cannot get what I can know, that what my neighbors know. Are you getting the point? What happens in distance vector, that every neighbor shares what they know to others, right? So I may not have idea of this entire huge network, right? So these two issues are solved in this link state routing. Okay. So what is the first problem? That whatever the propagation is happening should be faster enough, and second is that you should get, if possible, then you should get the idea of whole network, instead of having just partition of, having information of partition of a network. Okay, what is the advantage of doing so? That also we will learn soon. Okay, fine. So what happens in this link state routing? There are 5 steps. Okay. First of all, whenever I'm a router in my network, whenever as a router I'm up, I'm in the network. What will I do? Suppose, so what I will do, I will first discover my neighbors. Who is my neighbor? So actually, when I say discover my neighbors, that means what exactly I want to learn from them. Discover my neighbors, that means what actually I want to discover. As a router, I am up in the network, I don't have anything, my memory is totally empty. What I want to learn, who my neighbors are, what exactly I want to learn from my neighbors. Think, you use your mind, what exactly I want to learn from my neighbors. Who my neighbors are, how to identify my neighbors, how generally we identify the machines. IP address, shortest distance. That is the next question, Priyank. Who my neighbors are is not shortest distance. Yes, Cable and Hasti are correct here. I want to know which machines are in my nearby area. Okay, so yes, first of all, I will learn the network address. How to learn the network addresses? Think how to learn the network addresses. So actually, as a network, as a machine, I have, suppose I am connected with two networks. Suppose this I am a router, right? Or if I am a machine, I am connected with, I am connected through a network, or rather, I should say, I am connected with, I have two neighbors. Assume I have two neighbors, this neighbor and this neighbor. These are my two neighbors, and I am connected with them. I want to know who my neighbors are. So what I will say hello here, and I will say hello here. To my all interfaces, my physical interfaces, I will send my hello packet. Hello packet is what? That just a packet with source address, destination address will be broadcast address, right? So I will add my address and I will broadcast the packet to my both the interfaces. Then the reply of this hello will come. What it will contain? The reply will contain that who is the host here. I mean, who is the source of that reply? Who is the source of that reply in that IP address I am going to get? So reply of hello packet will contain that who has sent this reply, right? Because it will be the source of that reply, right? And in that packet from the source address, I will come to know, okay, this is my neighbor and this is my neighbor. IP address of the. So in short, if you don't want to go in that detail, simply the things that when you are up, then you will send hello packets to your neighbors through your interfaces and they will reply. In that reply, they will add their IP addresses and hence you will come to know that who is your neighbor, who are your neighbors. That means you will learn your network address. So now what I have in my table, I know that my neighbors are saying, I am saying this machine is X and this machine is Y. I will know that okay, X, that means IP address of X, and I will know my IP address of Y. So this is what information I have. What is the next thing that I will like to know? What is the next thing that I would like to know? That how I can reach them, as Priyank suggested. What is the distance? Now, distance is not necessarily in terms of meters. It can be in terms of delay. It can be in terms of actual meters. It can be in terms of number of hops, right? It can be in terms of what you can say, um, uh, uh, the queuing delay. It can be in terms of anything, right? But here the case taken is delay or cost. How to reach, what will be the cost, economical cost that I will have to pay. Any metric you can use to know about this. So what you will do, suppose I am taking the metric of delay, right? So what I will do, I will send another packet to X. I will call it as eco packet. What is eco packet? Eco packet is that it will get as it is, it will get reflected back from the next machine, right? So I will send eco packet to this machine and it will get reflected back. Now, if my cost is delay, whenever if I want to measure that how far X is in terms of delay, how much delay I take to reach to X, then I will start my clock when I will send my packet, eco packet, to that. It will come back and it will, whenever it will come here, right? It will come here. I will measure the delay, and whatever the delay that I will have, divide by 2 will be the one delay, one directional delay here. Okay, so that will be the cost, that will be the delay. Of course, you can have average. Suppose I am sending 10 eco packets and every time I am measuring the delay, the round trip delay I am measuring, and then divide by 2 will be the one directional delay. And 10 all 10 on all 10 delays can be averaged out to get the tentative idea of the delay, right? So that is one possibility, right? So in that way you will send eco packets. So next step of your link state routing is what? That uh, uh, that let us measure the cost, and for that send the necessary packets. For the delay it will be eco packets, right? So that will be your next step. So now what I know, that I know that what is the cost to reach X. Say it is 10 milliseconds, say it is 15 milliseconds. That type of output I am having here, right? 10 millisecond and 15 millisecond is the cost, suppose, is to reach to X and Y. Okay, so that is a step 2. Now it is, sometimes we'll say, okay, suppose it is delay. So things are not that much easy, right? It is possible that you are considering the queuing delay, right? whether that how much if I'm you are just considering the propagation delay, or you are considering the propagation delay plus queuing delay, or you are just considering the queuing delay. What is queuing delay? Queuing delay is that how much packet has to that how long the queue is for this interface, how long your packet after getting generated, whenever it has to be transmitted on this interface, it has to be placed in the queue for this interface, right? And then when it will pass through the queue, when it will come to the top of the queue, at that time it will get transmitted and it will get processed here and will come back. Okay. And you have to measure the delay. Now two things you have here, that whether you want to consider the queuing delay or not, right? If you will consider the queuing delay, what will be when you will start your timer? As soon as the packet is generated, you will start your timer, right? And if you want to avoid this queuing delay to consider, then as soon as your packet is generated, you will not start your timer, but you will start your timer when the packet comes on the top of the queue, when it will get propagated on this line. At that time you will start your timer. So what you are ignoring here? You are ignoring the queuing delay time here. Okay. So total delay minus queuing. In that way also you can consider, but yes, so what we are considering here is what we mean by queuing delay. So see, again, that I cannot say that the queuing delay, to consider queuing delay is a good case, or not to consider queuing delay is a good case. That depends on your application, how your network is arranged. That depends totally on the network administrator's thinking and the requirement, right? But the point is that your metric can be anything. It can be delay, it can be cost, it can be number of hops, or anything. Even in delay, it can be just propagation delay, or it can be propagation delay plus queuing delay, or anything, right? That is what the point is. Okay, but suppose it is queuing delay. Suppose I am considering queuing delay. What exactly I am considering? Queuing delay is what? When the queuing delay will be high, when the load is high on this line, or when the load is low on this line. When the queuing delay will be high, when the load on this line is high, or when the load on this line is low. When the queuing delay will be high. What is your take on this? When the load will be high. Yes, so when the load is high, at that time queuing delay will be more, right? So that is one idea that you should keep in your mind. Actually, when you are considering queuing delay, that means actually you are considering the load over this line. Now, whether to consider the load on the line or not, that is a separate issue. How it is a separate issue? That I am telling you. Like, suppose this is a situation, suppose this is a scenario. Two subnets we are having. Suppose I want to communicate. I want to find out route from this subnet to this subnet, right? Suppose I am considering queuing delay, right? That means I'm considering load on the line, and I have two options to reach to from this host to this subnet to this subnet. Okay, so now suppose I'm assuming most of the traffic is using this one, right? If I'm most of the traffic is using this line, assume that means load on this line will be high. Now assume that in my link state I'm considering the queuing delay. That means I'm considering load on this line. So what I will come to know, that if I want to reach from this subnet to this subnet, because queuing delay is considered, that means load is considered on this line, and hence what I will conclude, because I have two options, this option is better. That is how I will conclude in future, right? Because I'm considering the load. So what will happen now? Entire traffic that was going from west to east now will flow through this one. Why? Because now, according to my calculation of high load, I consider that this path is better. Okay, so now what will happen in future? That entire traffic will flow through this one. So again, now what will happen? Now this, whenever now new calculation will come, at that time, because I am considering queuing delay, this line will be considered the heavy line, and the path that will be considered better will be this one. So now what will happen? That entire traffic from west to it will pass through this one, right? So what will happen? And then again this line will be busy, this line will be occupied, then again entire traffic will pass through this one. So actually my traffic will get oscillated. It will either, once it will, entire traffic will flow from C to F, or it will flow from E to I. So it will keep oscillating, and it is not a good sign. That traffic cannot keep oscillating like this, right? So that is a problem if I am considering queuing delay, right? So if you are considering queuing delay and if you don't like to have this type of oscillation, what is the option that you can think of? That let's divide the load on, because I have two options. Let's divide the total load 50% over here, 50% over here, right? If I have two options, then I let us divide the load, and this is a better idea to handle this. But again, this is not the optimum or efficient use of the capacity available. But anyway, but this is still better than oscillating the traffic. Okay, so what is the point here? Like considering queuing delay is not when you will implement practically, but then yes, priority based dividing. So that is what my point is. Yes, true. Like what is the point here? That you have to add some additional practical solutions to the issue. Point is what? Whenever you are measuring the line cost, we cannot say that particular method is the best one or particular method will work everywhere. Whenever you will implement, practical time issues are going to come and practical time solutions you need to provide. Okay, so this will not be efficient and sufficient one. Okay, so that is what our point towards this algorithm is. Okay, what this says, this actually the first step, learning about the neighbors. So whenever this example already I have given to you, this is given with the more one. Like C wants to, if C wants to know about this neighbor, it is going to send hello packets here, here, and here. Whenever it is LAN, you can consider that LAN, you can think of it is nothing but like it is a all are connected with a node kind of thing. You can think here what is the point here? Like what you will think, suppose C wants to know about its neighbor, it is going to send a packet over this line, and on this line. That means to all machines over this line. Okay, but if you don't want to see in that way, you can see like LAN is nothing but a node and you want to know information from your neighbor, right? But neighbor is nothing but your neighbor is itself is a LAN of multiple machines. Okay, so that is what the point is. In short, learning about the neighbors, send hello packets from all your interfaces. Then it can be a machine or it can be LAN. No issues. If it is a LAN, all the packets from the LAN will reply you. All the machines from the LAN will reply because they are actually your neighbors only. Na? They are your neighbors anyway on that interface. So no issues about that. Okay. Now what I know some information about my neighbors, right? But now what is the next step then? The next step is that construct the packet using that what you have just learned. What you learned, who is your neighbor and what is the cost to reach your neighbors. So that is your third step, that building link state packets. Link state packets are what? That for each source, suppose this is my source A will know that about its neighbor B and E. B and E my neighbor by first two steps, and it will know that what is the cost to reach B and E by second step. Okay, same way B will generate a link state packet. It will inform about A, C, and F, and their cost. Same way for all other one. So what is my third step? Third step is also very simple. That construct the packet telling that what just construct it that what you already have learned. Okay, this will generate that what. So suppose this is my machine T. That machine T will generate a link state packet that is X and how to reach X and how to reach Y. Okay. Now what is the next case? No, see, I'm coming to Urjit. I will come to that point. Yet I have not discussed that one. Right? I will come to that point. Okay. What I have discussed so far up to this, everyone is clear? I have not discussed these 2 points yet. Otherwise, it is clear that all the packets, link state packets, what are link state packets? Everyone is clear with this? Okay, that's great. Okay, now fourth step is that send this packet to all routers. What I need to do, this is how it is different from distance vector. What I need to do as a machine A, I want to send this whatever I have, a link state packet. I don't want to send to my neighbors only. Because I have learned from the neighbors, so I will not send that thing to my neighbors. Whatever I learned, that is from the neighbors. So why to send them to again? What I want to do is that whatever I learned, I want to send to all in the network. That means I want to broadcast. What I know that should be known to everyone. How to broadcast? What are the options to broadcast? How can you broadcast a packet? Which routing algorithm you will use for broadcast purpose? For broadcasting, which routing algorithm will you use? Flooding, na? See, shortest distance is what? Cable. I need to know that who is my, see, what I know currently, my neighbors are B and E. Do I know that who is my other neighbor, how to reach them? Shortest distance is what I need to know, that how to reach C. For that I need this graph, but I don't know. What, as a router, I am just up and I have this information only. Yes or no? So which routing algorithm I will use to inform all other in the network? Okay, so I will send that to all my neighbors. So I will use flooding algorithm. So what is flooding? Flooding for sending link state packets. I cannot use any other algorithm. We want to do. We want to generate shortest distance. We want to find out shortest distance. That's why we are using this algorithm. If you already have that, no meaning of using this link state. Okay. So now link state packets are flooded. So all the machines will flood the link state packet. So every machine will receive the link state packet from every other machine. So now A will receive that who is the neighbor of C. A will receive who is the neighbor of D. A will receive who is the neighbor of F, and it has its entire information. In the same way, all the machines in the network are having all the information with them. Right? So now whenever it is flooding, we need to dam the flood. Do you know that we need to dam the flood? We need to dam the flood. We need to control the flooding. Otherwise, it will be infinitely long process. So how to dam the flood? What are the options we have for the damming the flood? How to dam the flood? Have you studied this method of damming the flood? Hope counter, true. Hope counter is what? True, hope counter is the solution. What is that hope counter? What is that hope counter? Counting the hope that which packet pass fixed number of hopes to visit. True, both of you are correct here. So can I say it is like a TTL? It's kind of TTL, right? Can I say it is kind of age, that how long your packet can survive? How many hopes your packet can survive? It can be in terms of number of hopes, then it will be TTL. If it is in number of time or number of second, then it can be age of your packet. It cannot be older than, or it can get older for 60 seconds only. After that, it cannot survive, right? So age is that. What is age? To dam the flood, right? So we have age of packet. It can be in terms of number of hop. It can be in terms of seconds. Like your link state can survive. Link state packet can survive for the 60 seconds only. After 60 seconds, it has to get discarded by all the routers. It cannot move further. The reason is that only that to dam the flood. Urjit, are you clear with this? Okay. Now, sequence number. What was the sequence number? Importance of sequence number? What is the importance of sequence number? Do you remember that we need to keep the sequence number? Suppose sequence number K is maintained in my routing table. What I will do with the, yes, to avoid duplication. To avoid the duplication. So again, it is these two fields are for the to damming the flood, right? So suppose I have maintained in my routing table K is my sequence number. That means if I am receiving K minus 1 packet, what I am going to do is I am going to discard it, because already I have seen the packet K. Okay. And what about this age? Age is for the limiting the age of your link state packet. Okay. Now, few issues, as I told you, whenever you will go for the practical implementation, the things will get a little bit complicated than what we study in the theory, right? So now the issues are associated with the sequence number as well, right? What wraparound issue? Suppose I am using just 4 bits, right? So what will happen? The wraparound will happen quickly. right? So 4 bits, that means only 0 to 15 can be your sequence number, right? Then after 15 again it will go to 0. So it is possible that you will not be able to identify that it is the 16th packet and hence 0, or it is original 0, right? So I hope you are getting the case. Suppose I in my routing table I have 0. What is the meaning of that? I have to accept 0th packet, right? In my routing table, if I'm maintaining that I can accept 0 or more, right? But actually now if then wraparound happens, then when 0 comes, 0 is actually the 16th packet. So now when the sequence number 0 comes, I will not be able to know which is older 0 or the newer 0. And suppose now 11 comes, so 11 is the older packet than previous packet than 16, but 16 has the cost, 16 has the number 0 now. So what will happen, what this router will understand, okay, it is 11th packet, that means it is a newer one than 0, and hence this will be discarded and this will be kept, right? So wraparound is a bigger issue, but how to solve that wraparound issue? By keeping this value larger. And generally this is kept 32-bit long, so it is sufficiently large to have to happen that wraparound of the sequence number. Okay, so are you clear with the issue of the wraparound, all of you? Issue of the wraparound is clear to you? Okay, next issue that can happen with the sequence number is, suppose my sequence number stored is say 4-bit long. For understanding, I am keeping it 4-bit long. So actually I have seen that I have seen the second packet. So far I have seen the second packet, and that means my the k is my 2, right? But now my next packet comes and its sequence number should be actually 3. What I am expecting, that next sequence number will be 3, but what I am receiving here is this bit of my sequence number is corrupted in my packet. This bit is corrupted, right? Instead of 0 it becomes 1. So now which number is this? This is actually 11, or we can say it is B, right? It is B. So now what will happen to my router? Actually it has value 2 now. So what it was doing, it was rejecting all the packets equal to 2 or below 2, right? What if we just use a bit to record that it is new one or older one, then the hardware will be less complex. I'm not clear with your point, Harsh. Can you elaborate that? You just a bit to record it is new one or older one, then hardware will be less complex. Already we are using the bits only, na Harsh? We are using the software only. We are just maintaining it. We are not keeping that in hardware. Hardware will be required to identify the things, to check the bit values. Otherwise, who will check that, right? But we are using bits to make sure that that hardware can identify that whether this is a new one or older one. I'm not clear with your question. I'm not sure whether it is answering your question or not. Harsh, you can elaborate. You can unmute yourself.
Yes, ma'am. My question is that, like, instead of using 32 bits, we'll use just 4 bits and an extra bit, which will indicate that whether it was like a new one or means it is a older one only.
Okay. So you want to use
1 and 0. Yeah.
So here the two problems can take place here. See, flooding is a huge process, right? Actually, in flooded, what will happen? It will not be like just 32 packets. Suppose, okay, so next step around will happen at 32 packets, right? Not at 16 packet, but at 32 packet, the next rep will happen. So again, at the time after 32 packet, that issue can take place once again. Why?
Yes.
Because flooding is a huge process and lot many routers are involved in that, right? So it is possible that after even few minutes the older packets can arrive. So it is possible that wraparound cannot be sufficient for this 4 bits and one more extra bit even. And plus, here two things you need to check: one extra bit that you need to verify, and then you need to go for this 4 bits even, right? And then also it is not providing you the solution, right? So if it is a larger one, then only this is going to help you in the better way. But again, if a network is smaller and this much is sufficient to handle, then of course you can go with that method. But Again, there is no restriction to have these methods, but what I suggest is that 32 packets are even not sufficient, because every second a packet is generated, 32 seconds are sufficient to generate 32 packets, right? So and in flooding, what happens after a few minutes, even the older packet comes, because it is for the huge network. In some from other areas, from the far areas of the routers, the packets can arrive after even some time even. Okay, so is it clearing your doubt, Harsh? But
Yes,
if it
ma'am.
is a smaller and controlled and maintained network, then of course any other method can help. But we are deciding for the internet and the huge network, right?
Yeah. Yes, ma'am.
One more issue is that okay, okay, more issues on the sequence number. Actually, we on sequence number and all we will cover in the laboratory session itself. Today we have laboratory session, so these 2 points we will complete in the laboratory session, and then after we'll start our experiment. So okay, let us now solve the doubt of Priyank, and then we will continue our discussion in the laboratory. This algorithm more complex than flooding because it includes with flooding more steps like neighbors and all. See, flooding is used for sending the data. Currently, we are using flooding to make a routing table so that we can send the data. Priyank, once I have the data, I will flood, I will broadcast it so that everyone will get the data. Here, I am not sending the data. What I am sending is link state packet. Link state packet, after receiving the link state packet and doing all this task, I will have a routing table. And using that routing table, I will send the data. Right? In flooding, we are just sending the data directly using the flooding itself. So we are making use of flooding to send the link state packet instead of data, so that we can create a routing table which can be used to send the data. Is it making sense, everyone? Okay. So now these 2 points are remaining. We need to discuss them in detail, right? 4 and 5, but we will discuss them in the laboratory session today itself. Okay. Then we'll start our experiment. So for now, you may leave, and any doubt you can ask me today in the laboratory session itself.